Let's sketch the given function f of x is equal to x cubed minus 9x. Let's determine the degree of the polynomial. The degree of a polynomial is the greatest exponent on x. We have f of x is equal to x cubed minus 9x. So the greatest exponent on x is 3. So the degree of the polynomial is 3. Let's determine the end behavior of the graph of the function. To determine the end behavior, we need the leading coefficient a sub n and the degree of a polynomial n. From the previous part, we know that the degree of this polynomial is 3. Let's find a sub n, in this case a sub 3. Because f of x can be written as a sub 3 times x cubed plus a sub 2 times x squared plus a sub 1 times x plus a sub 0, and we have f of x is equal to x cubed minus 9x. X sub 3 is equal to 1, a sub 2 is equal to 0, a sub 1 is equal to negative 9, and a sub 0 is equal to 0. So a sub 3 is equal to 1. Because n is equal to 3 is odd, and a sub 3 is equal to 1 is greater than 0, the end behavior is down to the left and up to the right. Let's determine the y-intercept, which means that x is equal to 0. We solve f of 0, which is equal to 0 cubed minus 9 times 0, which is equal to 0. So the y-intercept is 0, 0. Let's determine the zeros and their multiplicities of the function. Let's solve f of x is equal to 0. We have x cubed minus 9x is equal to 0. X times x squared minus 9 is equal to 0. By factoring, we get x times x plus 3 times x minus 3 is equal to 0. So we have x is equal to 0, x plus 3 is equal to 0, x minus 3 is equal to 0. X is equal to 0, x is equal to negative 3, and x is equal to 3. So the zeros of the function f are x is equal to 0, negative 3, and 3. Let's determine their multiplicities. Because each factor has 1 as an exponent, each has a multiplicity of 1. Let's determine the behavior of the function at each x-intercept. From the previous part, the zeros of function f are x is equal to 0, negative 3, and 3, and each has a multiplicity of 1. If a multiplicity is even, the graph of the function touches the x-axis. If a multiplicity is odd, then a graph crosses the x-axis. Because 1 is odd, at each x-intercept 0, 0, negative 3, 0, and 3, 0, the graph crosses the x-axis. Cross points are 0, 0, -3, 0, and 3, 0. Let's sketch the function using the information we got. So the end behavior is down to the left and up to the right. The y-intercept is the origin. Cross points are 0, 0, -3, 0, and 3, 0. From the end behavior, we can draw these two arrows. From these cross points, the graph has to cross the x-axis at these x-intercepts. Then we get the following sketch of the function. Because we do not know the maximum and minimum of the function from the information we have, the sketch captures a general shape of the function. Let's solve x minus 7 times x plus 4 times x plus 1 is greater than or equal to 0. The first step is to find the zeros of the polynomial. We have f of x is equal to 0. X minus 7 times x plus 4 times x plus 1 is equal to 0. We get x is equal to 7, x is equal to -4, and x is equal to -1. The next step is to split the entire interval using the zeros of the function. The interval from -infinity to infinity becomes -infinity to -4, -4 to -1, -1 to 7, and 7 to infinity. Let's pick a x value in each interval to see if the function is positive or negative. On the interval from -infinity to -4, let's pick -5. Then f of -5 is equal to -5 minus 7 times -5 plus 4 times -5 plus 1. So -5 minus 7 is negative. -5 plus 4 is negative. -5 plus 1 is also negative. So the function f of -5 is negative. By continuing the same process on each interval, we get the following results. Because we want to solve f of x is greater than or equal to 0, first let's determine the interval when f of x is greater than 0. The function is greater than 0 on the interval -4 to -1. It is also positive on 7 to infinity. F of x is equal to 0 at x is equal to -4, -1, and 7. So f of x is greater than or equal to 0 on the closed interval -4 to -1, union closed interval 7 to infinity.